Hi everyone. In this video, I will illustrate phase two of an observational study. This video is the second part of a two-part series about observational studies. This video is the continuation of the part one video where I did the exploratory phase, okay? Now in part two, I'm going to work on the matching phase. As usual, I already prepared an R notebook for this video, and I will share a link to this notebook in the video description, so you're gonna have access to the notebook. Couple of things about this notebook. First, similarly to the part one video, I already included all the code in the notebook because I really don't want to spend time kind of writing all the code live as I do the video because that would take me too long. So I'd rather spend the time explaining you guys what the code does and also helping you interpret the code output. Okay, so that's why you're going to see that all the code is already included here. One difference with respect to the first video is that in this video, I decided to write down every step I take and also every interpretation. Why? One viewer who watched part one noticed that in part one, I did not write down like the steps I was taking or the interpretations. So in part one, I explained it all verbally, okay? But I didn't write down anything. So I think this viewer's suggestion is valid. So that's why in this notebook, you will see every step and every explanation already written down, okay? Cool. All right, so let's jump into action. So first, we need to start by loading these two packages, tidyverse and DOS2 package, because of the same reasons that I explained in video one. Okay, so let's go ahead and load these two packages. Perfect. And the first thing I want to do, guys, is just kind of remind you of the main conclusion from the exploratory phase. So from video number one, this was our main conclusion. Okay. And this is the conclusion. The two groups, welders and non-welders, are unbalanced with respect to age. We found out that welders tend to be significantly younger than non-welders, okay? Now, before attempting to accomplish the goal of the study, and remember that the goal of the study is compare both groups with respect to their level of genetic damage. So before doing that, we should balance the two groups across all the observed covariates. So not only with respect to age, but also with respect to race and smoking status. Okay, so we should do that balancing. I will achieve this balance, as you will see in a second, by creating pairs of treated subjects, welders, and controls, non-welders, matched on their propensity score. So I'm going to do the balancing based on the propensity score. What is the propensity score? Propensity score is just simply, guys, the probability that an observation belongs to the treatment group given the values of the observed covariates. That's the propensity score. Now, the important thing about the propensity score, or the valuable thing, if you will, is this, what they call the balancing property, explained by Rosenbaum. Okay, the propensity score has a balancing property, which means that this is very, very important. If we form the treatment and control groups by pairing observations with similar propensity scores, the two groups will be balanced across all the observed covariates. So that's amazing. So if you do the matching of the treated subjects and controls using the propensity scores, you should expect that the two groups will be balanced across any of the observed covariates. That is great. Okay. If you wanted like a more technical explanation of what it means, this is a more technical framing of the same idea. We can say that if we form every pair of treated and controlled subjects by matching them for the propensity score, the probability distribution of all the observed covariates will be the same. Okay, so the groups are similar with respect to the propensity scores. They will be similar with respect to the probability distribution of any observed covariates. That's great. Okay, so in summary, matching by propensity score allow us to do the matching based on a single indicator, the propensity score, okay, rather than attempting the computational difficult task of matching for every observed covariate. And this is really like if you attempt to match for every observed covariate, it's going to be difficult because in this case, you need to match, you need to make sure that you have a match based on race, based on smoking status, and also based on age. So three things. So you need to take care of three things when you're doing the balancing. Okay, and this is actually a kind of a toy example. So in real life examples where we have more covariates, like sometimes dozens, attempting to do a balancing simultaneously across all the covariates is really, really, really difficult. With the propensity score, we only need to use the propensity score to do the matching. Okay, so that's an amazing property of the propensity score. So in other words, the propensity score allows us to do the matching very efficiently. Okay, cool. Perfect. So this is the thing. How how to get the propensity score? A propensity score. So we need to get the propensity scores. So the propensity score, as I told you earlier, propensity score for observation I, for any observation, is the probability that observation I belongs to the treatment group given the values of the covariates. Okay. Applied to this example, propensity score for observation I would be the probability that observation I is a welder, that's the treatment group, given that person's age, race, and smoking status. Okay. Now, how to get the propensity score, guys, for this problem or for any problem? Well, we can estimate this probability, okay, using logistic regression. Remember that logistic regression allows us to estimate the probability of any event of interest based on the values of a group of predictors, okay? And in this case, the event of interest will be if the person is a welder or not, okay? So in this example, we're gonna use logistic regression to estimate the probability that someone is a welder. So the probability that someone belongs to the treatment group, given his age, race, and smoking status. Okay. In summary, we can apply logistic regression to estimate the propensity scores, and that's what I do in this code cell. Okay. Um, okay, so here I am applying logistic regression by using the GLM function, general linear model function, specifying that the target is the welder column. These are the three covariates or predictors. Data is Costa. And the way, because you can apply GLM to apply many kind of models or to obtain many kind of linear models. If you want to specify that you are applying logistic regression, then you need to specify that the link should be logic. So the logic link is the link that characterizes the logistic regression model. Okay. Great. Now let's run this before I forget. So let's go ahead and run this, and then we're gonna store the output from logistic regression in that variable, logistic reg model welders. Okay, let me run it, and good. Now, as I said here, I can use the logistic regression model to get the estimated propensity score for each observation. Reminder that the propensity score for observation I is simply the probability that an observation is a welder given these three covariates. Now, this is the thing, guys. That's what I'm doing this right now. I want to store the propensity score for each observation in a new column in the Costa data set. To do so, I decided to create a new version of the Costa data set that includes this new column. So from now on, we are not going to work with Costa, with the original Costa data frame anymore. We're going to work with this Costa extended. Costa extended is just Costa plus a column with the propensity scores, right? And well, let's run this. Here we are just creating kind of a copy of the Costa data frame, and we're storing that copy in Costa extended. So let's run it. And now, next, I create this new column, propensity score welders, to store the propensity scores. Notice that I am creating that column in Costa extended, okay? So in Costa extended, I'm saying mutate allow us to create new columns, and the new column name should be propensity score welders. And what I'm doing here is this, it's kind of returning the probabilities, okay? This is what we should know. To get the probabilities from a logistic regression model obtained using GLM, that's what we did, we need to use the predict function, okay, on the model. So we are invoking the predict function on the model, but we need to set type to response, okay? Like if you want to retrieve the probabilities from a logistic regression model, type should be response, okay? So this will give me the probabilities. I will store the probabilities in this new column uh, in this data frame. But if I want to make the change permanent, I need to assign all of that operation back to the data frame. Okay, that's why I'm assigning all of this operation back to the data frame, Costa extended. Okay, let's run it. And now we can take a look at Costa extended, and you will see that Costa extended is exactly as Costa, but with a new column. Like if you remember from video one, Costa simply contains these columns, but now Costa extended also includes the propensity scores. Okay, cool, excellent. Now we have the propensity scores, and we can now go ahead and do the matching. This is the thing, guys. I'm going to do the matching using optimal matching. There are many methods to do the matching. Optimal matching is one of the most widely used methods because it's actually one of the best ones. Okay. Now, what is optimal matching described according to Rosenbaum? Optimal matching finds the set of matched pairs that minimizes the total distance in propensity scores across all pairs simultaneously, as opposed to a greedy matching, which matches pairs one at a time without reconsidering earlier matches. So a kind of a common intuitive way of doing the matching would be this greedy matching. Like greedy matching means, okay, so treated subject number like the smallest distance in propensity score is between treated subject number 3 and control subject number 5. So let's match those two observations, okay? Because they have the smallest distance in propensity score. The second smallest distance happens between treated subject number 7 and control number 11. So let's match those two. So that's greedy matching. So you match each pair one at a time, but you don't reconsider earlier matching. Optimal matching is a kind of non-naive and really not non-straightforward approach that tries to minimize the total distance in propensity score across all pairs simultaneously. So the algorithm behind optimal matching, like to program the algorithm behind optimal matching, requires a lot of effort. Okay. So it's not a straightforward algorithm, okay? But thankfully in R, as you will see, we have a function, couple of functions actually. So not only one, a couple of functions that allow us to apply optimal matching, okay? All right, so let's go ahead and apply optimal matching. And the function that we're going to use, it's pair match. There are a couple of more functions, okay, to apply optimal matching, but I'm gonna go with this one, pair match. Pair match returns a vector assigning each observation to a matched pair. You will see that in a second. Um, okay, so this is kind of one clarification, so you don't get surprised by the results later. When there are more controls than treated subjects, like in this example we have 26 controls, 21 subjects, 21 treated subjects. Some controls will be left unmatched, okay? And they will get assigned an NA. So pair match will assign NA to the unmatched controls, okay? Now, to use pair match, we need to install and load the opt match package, okay? I already installed it, but if you want to replicate this analysis, you need to install it, okay? So to install it, you need to just remove the comment and run this code cell. I don't need to do it, I already did it. What I need to do is I need to load the package, okay? So I need to load the opt match package, which I'm going to do right now. There you have it. And now we can use the pair match function because that function is part of that package. Cool. Now, this is the thing, guys. That's another thing to consider. I mean, there are kind of several things to consider here. Rosenbaum recommends matching treated subjects and control subjects using the square differences. Okay. This is not like, if you don't do it like that, it's wrong, but it's kind of the standard recommendation. So don't do the matching based on the raw differences, but use the square differences. And he offers two reasons. The first one is the square differences incentivize the matching algorithm to avoid poor matches in a kind of stronger way than if you use raw differences. Okay, and here you have an example illustrating that. Okay, I think between the two reasons, that's actually the most important one. Okay, with the square differences, you are incentivizing the method to penalize poor matches even more. Okay, and the second reason is that Raw differences could be negative and positive, but square differences are always positive. And when it comes to a measure of distance, it's always better to have a measure of distance that is always non-negative. Okay, so that's the second reason. So I'm gonna go with that suggestion instead of raw differences. I'm going to use square differences. Okay, but I want you to know that it's also possible to use raw differences. Okay, again, it's not wrong. It's just more recommended to use square differences. Okay, so that's what I do next. Let's create a matrix with the square differences in propensity scores between treated subjects and controls. This is the thing. Before creating this matrix, we need to take care of something. This matrix, the matrix with the square differences between treated subjects and controls, should clearly label each observation with its corresponding index. So each treated subject and control should be labeled with their indexes in the COSTA data frame. And by COSTA, I mean the COSTA extended, same thing. All right. So each treated subject and control subject should have the right index. Okay. And that's why in this code cell, what I'm trying to do is I'm storing in these two vectors the indexes. So these are the indexes for welders, like when welder is yes, and these are the indexes for controls when welder is no, like non-welders. Okay, so these are the indexes because again we need to use those indexes uh, in the matrix with the square differences in propensity score. So let's run that, and when we take a look at this, we confirm that this is correct. So first, these are the indexes for controls, okay? And these are the indexes for the welders. That's right, because if you go back to the original data frame, to the COSA data frame, you will confirm that the first 26 observations are welders, and the last 21 observations are controls. So this is correct, okay? This is good. Perfect. All right, now we are ready to actually to apply optimal matching. Well, before applying optimal matching, we actually need to get the matrix, okay? And that's what I do next. That's a matrix of square differences in propensity scores between welders and controls. To get that matrix, I'm applying the outer function, and the outer function is just doing the following. The outer function is applying this ghost function, and notice that the ghost function just retrieve the difference, the square difference between two vectors, right? The difference, a square. So the square difference between two vectors. But what vectors? The two vectors that we pass as the first two arguments. What is that vector? What is the first argument? Those are the propensity scores for the welders. So using the indexes for the welders, okay? And the second vector will be the propensity scores for the non-welders, for the controls, okay? So outer will allow me to apply that function to compute the square differences between those two vectors. That's what I want. And sure enough, now when we take a look at this time matrix square propensity scores, we get a matrix where, it's gonna take a second, where we can see the this is, for example, the square distance between the first treated subject, the first welder, and every control. Okay, so I need to go down to continue to see this, but yeah. So the first row will be the square distance between the first welder and each of the control, each of the 26 controls. Okay. Okay, so that's the matrix with the square differences, and now we can actually apply pairmatch. Okay, now we can actually apply pairmatch. Okay, now we use the pairmatch function to do the optimal matching based on the matrix of square differences in propensity scores between welders and control. And here we are applying the pairmatch function. The first argument is the distance matrix, and this argument requires some explanation. This is the thing, guys. When we invoke the pairmatch function, we need to enter a value for the data parameter. Okay. Otherwise, the output from pairmatch may not, let's say, align with the output with the original data frame. Okay. When you do data equals COSTA extended, which is the data frame that we're using, we make sure that the indexes of the matched pairs returned by pairmatch will trace back correctly to the rows in the COSTA extended data frame. So this is mandatory. So we need to do this, okay? Okay, and notice that I'm storing the output from pair match in that variable, pair match square propensity scores, and this is the output we get. Okay, now how do we interpret this, guys? Well, easy. Notice that remember that the first 26 observations were controls, right? Notice that some controls will get NA. Why? Because of what I explained earlier. These controls were not matched to any welder. Okay. Now, how about this? What does this mean? So this control has 1.16. So this control will be matched with the welder with this matching score, if you will, or matching labels. These are not scores. These are labels. Okay. So 1.16. What do you see? 1.16 again. You see 1.16 right here. That means these non-welder, this control was matched with this welder. Okay. And now, for example, this 1.4. Where do you see 1.4 again? Over here. So that means that this control, this non-welder, was matched with this welder, and so on and so forth. So 1.10, where do you see 1.10 again? Over here. So that means that this non-welder or control was matched with this welder. Okay. Now we can use these matching labels. Okay, to actually accomplish our next step. Okay, and this is what we should do. Okay, we should use the information in this information. Okay, we should use the information in pair match square propensity score vector to create a new data frame. Now, this new data frame has special characteristics. Okay, I'm going to call this new data frame Costa matched, and that data frame, each row of that data frame will be a matched pair. Okay, so I'm going to create a new data frame titled Costa matched, where each row is a matched pair. To make it easier, I will create that Costa matched data frame in two steps. Okay. The first step is just simply, okay, so Costa match will be Costa extended plus one new column, the match group column. And the match group column will store this information. Okay. The match group column will store that information, guys. Okay. So notice that Costa match is just simply Costa extended with a new column, and the new column is I call the new column match group, okay, which is simply the the matching labels, okay. Notice that the match group column will store the information here, and what is the information here? The match label, okay. Let's take a look. Sorry, let's take a look at that. So let me create my Costa match, and when you look at Costa match, guys, is simply all of these columns, all of those columns are the same columns we saw in Costa extended, but now we have a new column, match group. Okay, perfect. Now, guess what? We can use this version of Costa match to create the final data frame that we're going to use. And for that, we're going to go to step number 2. This is the thing. Now we should modify Costa match, this this data frame, okay, to create a new data frame where each row is a matched pair. How are we going to do that? You'll see. Just one clarification. Um, in the new version of Costa match, okay, which you will see in a second, the column with the suffix underscore T store information for the welders. T means treated subject, okay? So anything with T means treated subject, welders. And columns with the suffix C store information for the control, non-welders, okay? Okay, so how do we actually proceed to the second step? The second step, guys, is simply, we're gonna split, okay? We're gonna split Costa match into welders and non-welders, and we're gonna join them by match group. Okay, so we're gonna split this Costa match into welders and non-welders, and we're gonna join those two sub data frames into a big data frame based on match group. Okay, so let's do it. This part right here, the first part, that right there. What am I doing there? I am retrieving the welders. Okay, I am retrieving the welders and all the information for the welders. So notice that I am filtering by welders. Okay, and one thing that I'm doing is, okay, instead of using the original column names, for example, age, I'm changing the name. So because here we are retrieving the welders, I'm saying no, no, no. This should not be called age. This should be called HT because we're talking about welders, treated subjects. So this should not be called race. This should be called race T because we're talking about the welders, the treated subjects. Okay. So this will create a data frame with the welders only, and the columns will have the T suffix. Okay. What am I doing after that? I'm inner joining that with, sorry, Control Z. I'm inner joining the welders with what? With the non-welders. Okay, so I'm inner joining their welder with the non-welders. Okay, I'm filtering and I'm saying like welders no. So, and how am I doing the inner join or using what column? What is the matching column that I'm using? The match group. So I'm doing the inner join using the match group column, okay? The match group column. Because of what I said earlier, like this 1.16 will be matched with this 1.16, okay? So the right column to the matching should be match group, okay? And guys, sure enough, you run that code cell, and then you take a look at the matched Costa match data frame, and ta-da, there you have it, okay? We have now, look, this is the first welder. Sorry. Sorry, right there. This is the first welder, okay? This is the information about the welder. So welder number one with this age, with this race, with this smoking status, and the DPC value. Remember, DPC evaluates the level of genetic damage. Match with this control. Okay, and then for the control, we also have the information, the index of the control, the age, the race, the smoking status, and the DPC. Okay, and notice that I discarded here. I discarded select, and then I use a negative match group. I don't want to see the match group here anymore. Okay, so I remove the match group. Okay, but yeah, definitely here we have now we have matched pairs, guys. Okay, now we have matched pairs. Okay, welder match with the corresponding control according to optimal matching. Second welder right there match with the corresponding control based on optimal matching. Okay, that's perfect. That's the data frame that we're going to use to do our two final steps. Okay. Now notice that I use capital letters here because this is important. Now that we have matched pairs, we need to confirm that the two groups are balanced for the three covariates. So before attempting to answer our final question, remember that our final question is this. Guys, don't forget that. Our final question is this. Um, compare both groups with respect to their level of genetic damage. Okay, that's what we want to know. Okay, before doing that, before attempting to do that, we need to do a final check. Are the matched pairs balanced? Okay, are the matched pair balanced? And that's what we're going to check. Okay, let me take you back here. Okay, one more time. Now that we have matched pairs, we need to confirm that the two groups are balanced for the three covariates. Okay. And to check for balance for the three covariates, I will basically repeat the same analysis I did in video number one when I checked for imbalance between the two groups. Okay, so you watched video number one and you saw how I checked for imbalance between the two groups with respect to age, race, and smoking status. I'm gonna repeat the same thing here. Okay, so that's why from now on I'm not gonna explain the code because I already explained the code to check for imbalance in video number one. Okay, but the bottom line is, let's check if the match pairs give us actually balanced groups. And if they do, then we can proceed to answer the final question. Okay. Excellent. Let's go ahead and do that. Okay, so let's check for possible imbalance in age after matching. First, as in video number one, we start by computing some summary statistics. Okay, so let's take a look at the summary statistics. Here we can see that the average age for treated subjects for welders is 38.8. For control is 40.1. The median age for welders is 38, and the median age for for non-welders is 40, okay? Now, how does this compare to before matching, okay? Well, before matching, welders were 4.5 years younger on average, but right now the difference has reduced to 1.9. So the difference between this and this, between these two means, is only 1.9. So the difference have reduced. The average difference have reduced, but not only that, the difference in median has also reduced. Before matching, the difference in median was 3.5, but now it's only 2, okay? Difference between 38 and 40 is only 2. So the difference in age between the two groups after matching um, has reduced. But has it reduced to the point that the difference is not significant anymore? That's what we want. That's the ideal situation, right? Well, let's go ahead and check. Is the difference in age between the groups statistically significant? So to do that, or to check for that, we're going to run a Wilkinson rank sum test, which is the same test we run to check for the difference in age in video number 1. Okay, couple of differences, guys. Notice that pair here and here we need to set pair to true. Why? Since we used optimal matching to pair each welder with a non-welder, we must apply the paired version of the Wilkinson rank sum test. In video 1, the observations were not paired. So that's why we use the kind of a standard independent sampling version of the Wilkinson rank sum test. But here, we need to use the paired version of it. Okay? How about this exact false? Well, that parameter exact controls whether an exact p-value should be computed or not. And here I'm saying that exact false, no. I mean, here I'm saying that exact false, meaning like, no, I don't want to compute an exact p-value. This is the thing, guys. Exact p-values are kind of the right choice when there are no ties in the data. Okay. However, ties are likely to happen with respect to age, right? So this is a test to compare the age between the two groups. It's kind of not surprising to find welders and non-welders with the same age. So we should expect to find couple of pairs, few pairs with the same age. So we should expect ties. So that's why in this case, uh, since ties are expected, we should not use an exact p-value. So when we set exact to false, the Wilkinson rank sum test compute the p-value using the normal approximation, and the normal approximation is the right way to compute the p-value when ties are expected. Okay, great. So let's run the Wilkinson rank sum test to see if the difference in age is significant after matching. And ta-da! Basically, we can, just directly focus on the p-value. And this is the conclusion, guys. If we use an alpha of 0.05, which is kind of the standard alpha, p-value, that number, is greater than alpha, right? So we do not have evidence to claim that the difference in age is statistically significant, okay? P-value greater than alpha, not statistical significance, okay? So interesting, guys. So whereas before the matching, the two groups has a significant difference in age, you can refer to video number 1, they do not have such a difference anymore after matching, okay? So the difference is not significant anymore. So matching removed the significant imbalance in age. Great, that's what we wanted to do, okay? Excellent. So how about the imbalance in race after matching? Let's see. So I'm gonna kind of do the same thing I did in video number 1. So summary statistics. And these are the percentile of each race among controls, okay? Among non-welders, okay? So among non-welders, we have 10% African Americans, 90% Caucasians. That's among non-welders. How about among welders? Same percentages, the same percentages. So among welders, 10% African Americans and 90% Caucasians. Okay, so what is the conclusion? If you remember in video number 1, there was a difference in the race status between the two groups. Okay, but the difference was not significant. Okay, so if you remember video 1, the difference in race was not significant, but there was a difference. Okay, at least there was a difference. Okay, now after matching, the difference was fully erased. The percentage of each race is exactly the same in both groups. Okay, so matching erased the difference completely. Again, the difference in race was not concerning because it was not significant, but now you can see that matching makes the situation even better. Okay. How about the difference, the potential difference in smoking status? So again, I'm gonna compute summary statistics first. So this is the smoking status among controls, among non-welders. So let's focus on the smokers. Among non-welders, 38% of smokers. And how about among welders? Among welders, 52% of smokers. Okay. So how does this compare to before matching? Before matching, 52% of smokers among welders and 35% of smokers among non-welders. Now the difference has reduced a little bit. Okay. The difference of in smoking status has reduced a little bit after matching because now after matching, 52% of smokers among welders and 38 among non-welders. So it has reduced a little bit, 52, 35, 52, 38. So the difference has reduced a little bit, okay? But the conclusion is, even after matching, there is still a difference in a smoking status. But this is the thing. This difference is not concerning, guys, because it's not statistically significant. So it was not statistically significant before matching, and as you will see now, it's not statistically significant even after matching, okay? How do we check for that? Well, we apply the McNemar's test. One important thing, guys, in video number one, to check for difference in smoking status between the two groups, we apply the Fisher test. But here we need to use McNemar's because we have matched pairs. So Fisher is valid for independent samples, but here we have pair samples, so we need to use McNemar's. Okay, so McNemar's is the pair sample version of the McNemar's allow us to apply the pair sampling version of the Fisher test. Okay. Okay, when we run McNemar's test, we get this p-value right here, this p-value. So what's the conclusion? Alpha 0.05, p-value 0.50. Obviously, p-value greater than alpha. So similarly to before matching, we conclude that after matching, the difference in smoking status between welders and controls is not statistically significant. Perfect. So now we have found out that there is no imbalance in any significant imbalance in any of the covariates after matching, okay? And that's the conclusion that we arrive at, okay? It's the partial conclusion that we can arrive at so far. Okay, the two groups do not exhibit an imbalance relative to any covariates, but they did relative to age before matching, okay? So that's why we had to do all of this matching, okay? Before doing the matching, the two groups differ significantly with respect to age. Not anymore. Not anymore after matching, okay? So since after matching, the two groups are comparable, we should compare them with respect to the outcome variable to answer the original question. And what is the original question? One more time. The original question was this. Find out if being a welder influences the level of genetic damage. And remember that the level of genetic damage is measured using the DPC column. We accomplish this by comparing the genetic damage between the two groups, the welders, the treatment group, and the non-welders, the control groups, okay? So let's do a comparison, and to do a comparison first, I'm gonna get some summary statistics, okay? This is the level of DPC for for welders, okay? For welders, so the treatment group. So this is the average DPC level for welders, 1.9. The median DPC for welders, 1.4. How about non-welders? Should be lower. Is it? Yes, it is. Okay. For non-welders, the average DPC is 1.2. For welders, 1.9. So, and the median for welders, 1.4. For non-welders, 1.1. So we can see that based on the summary statistics, based on the descriptive statistics, so the level of DPC seems to be higher for welders. Uh, Statistically higher, so is the difference statistically significant? Well, let's go ahead and apply Wilkinson rank sum test, okay? Now we apply again Wilkinson rank sum test, but again, the paired version of the Wilkinson rank sum test, but to compare the DPC level. So earlier we applied Wilkinson rank sum test to compare the two groups with respect to age. Now we are comparing them with respect to DPC. Is the difference significant? Is the difference that we are observing here statistically significant? And it is. You will see that this is the p-value. So that p-value is actually less than alpha, guys. So if we use an alpha of 0.05, p-value 0.0258 is less than alpha. So the difference in DPC between welders and non-welders is statistically significant. Moreover, since the alternative hypothesis is greater than, don't forget that here the alternative hypothesis is greater than, okay? So we can say a little bit more, okay? Since the alternative hypothesis is greater than, we can claim that the level of DPC among welders tend to be higher than the level of DPC among controls, okay? So not only can we claim that, yeah, there is a difference, there is a statistical difference between the two groups, we can say a little bit more. No, we can claim that for DPC, I'm sorry, for welders, the DPC level is higher than the level of DPC for controls. Okay, perfect. So what is the answer to the original question? Well, the output from the Wilkinson test gives us evidence to claim that being a welder increases genetic damage. In other words, we can claim that the treatment influences the outcome variable. Okay, and that's the end of our matching phase, and that's the end of the observational study analysis, guys. Now, briefly to kind of summarize what we just did, okay? Like the few steps that you need to consider when you're doing the matching phase of an observational study. In the matching phase, guys, you start by computing the propensity scores using logistic regression, right? That's what we did. Then you use the propensity scores to obtain a matrix like you should obtain a matrix with the square differences. I mean, you can obtain a matrix of with the differences in propensity score, just like the raw differences, but it's more recommended, remember, to obtain a matrix with the square differences in propensity scores. And what do? Then you feed that matrix to the optimal matching algorithm, okay? The optimal matching algorithm will return what? The matched pairs. Then you use the match pairs to do what? You create a data set where each row is a treated subject and all its data together with its corresponding match control and all its data. And now you use that data set with the match pairs to confirm that both groups are balanced. So before attempting to answer the final question, you need to check using that data set with the match pairs that both groups are balanced with respect to every covariate. If they are balanced, like in this case, you proceed to compare the two groups with respect to the outcome variable. If they are not balanced, then you need to use a different matching strategy, okay? If they are not balanced, you need to use a different matching strategy. But in our case, after applying optimal matching, the two groups were balanced, so we went ahead and then compared the two groups with respect to the outcome variable. And then once you compare the two groups with respect to the outcome variable, if you find that the two groups are statistically different with respect to the outcome variable, that's what happened to us, then you might go ahead and conclude that, you know what, the treatment influences the outcome variable, all right? So those are kind of the steps you follow when you're doing the matching phase of an observational study, okay? Okay, guys, so that's all for this video. I hope you learned a lot about observational studies and especially the matching phase. Thank you for watching, and I will see you in another video. Bye.